Maybe I will introduce the name of the LPBF 316L in different standard. The additive manufacturing method have different name like PBFL, like LPBF, okay, and SLM. So they are same additive manufacturing technology. Okay, next I will introduce myself. My name is Yefeng Chen from Wuhan Institute of Technology. Uh, this part of work is finished in Nanjing Tech University. So I will acknowledge my thanks to my home university. Okay. Uh, I will first introduce the background. Uh, this research is based on the nuclear application of additive manufacturing. As you know, in China, the nuclear plant is very popular. Maybe many nuclear plant is shut down in Germany, in Europe, but it's very popular in China. And the mining technology have been applied in nuclear plant, and the AM, the additive manufacturing is also introduced to the nuclear plant. But there is a very big gap between the new technology and the base demand, because nuclear plant is very dangerous and its demand is high safety and high reliability. But our new technology has instability. So I want to discuss the gap between them. Okay, I will introduce this manufacturing technology, the LPBF, and the most advantage of the LPBF is rapid manufacturing and high accuracy and low cost of time and money. So it has been used in nuclear plant for some important component in China nuclear plant. And the material is 316L stainless steel. So, but we all know in additive manufacturing material, it has obvious anisotropy in mechanical property. This is a tensor curve of different direction, different build direction. The strength and the elongation is different. And so, besides the low cycle fatigue, which is very popular in nuclear plant, the LCF low cycle fatigue property and corresponding fatigue reliability is also different for different building direction. So we have conducted many tests on this material. This material is based on the commercial standard process parameter and commercial stainless powder to fabricate different orientation samples and conduct the LCF test on each at high temperature, 550 centigrade. And we have conducted many micro hardness and indentation on different surface, the top surface and side surface or not lateral surface. Okay, we can see the tensor probability and the hardness. The side, the top surface, the micro hardness on the top surface is the max. Is higher than the side surface and much higher than the traditional 316L. And their tensor curve is also different. So we want to know why. we use the EBSD model to characterize the grain morphology and the texture direction. We have found obvious texture in the as-built materials. The 110 direction is parallel with our building direction, and this texture lead to the difference in tensile property. Okay, next is about the LCF property. The left is the horizontal spaceman data, and the right is the vertical spaceman data. We can see that they all exhibit cyclic softening behavior. This is mainly due to the high density dislocation annihilation. And we use the coffee meshing bus-stream model to related the stream amplitude and the fatigue life. We can see that there is a larger dispersion in vertical spaceman. Okay, this is the degree of softening, because they have a texture, so the degree of softening is different, and the plastic strain energy is also different. The vertical spaceman exhibit significantly higher than plastic strain energy, consistent with their lower stress and shorter fatigue life. And this is the fractal surface. We can say that the vertical spaceman has larger internal defect compared with the horizontal spaceman. In our discussion, we think the internal defect is same, but the project area with different loading direction is different. So the dish-like shape of this defect result in larger projected areas and sharper edges on the vertical loading, significantly reduce the fatigue life and increasing the scatter compared with the horizontal loading. Okay, the final part is the most important. Is how to quantify the dispersion and determine the reliable boundaries. Because LCF test is a long-term test, the sample is very few. We can't get many data sets. So we need to analyze the reliability based on the small data set. Inspired by HCF reliability analysis method, we want to use the linear relationship and distribution model to quantify the dispersion. This is the model. It's a bus-stream and the Weibull distribution model. We can correlate it with the stream amplitude and the fatigue life. So this is the calculating process. We use optimization algorithm to calculate this three parameter A0, A1, and beta. If we get this three parameter, we can get the boundaries. The most important sentence is the most important conclusion is our additive manufacturing 316L is okay. It's worse than than traditional 316L. And anisotropy, isotropic characteristic between vertical and spaceman is very big. So our conclusion is that additive manufacturing method maybe can't be used in reliable applications. Okay, this is my study, and I want to thank to my supervision of Professor Xiaowei Wang and Jianming Gong, and much thanks to academic visit in Professor Walter's lab of TU Dortmund University. Thank you for your attention.